Okay, do you hear me?
Yes.
Okay, and you see the screen, right?
Yes.
Right.
Yes.
Okay, so we finished on the equation with one species. We have only one population, and we see that when we take into account the limitless of the resources of our environment, we involve these n divided by L to the equation, we get the stable equilibrium near the solution L. But all these models have a problem. If we consider, for example, mammals, we need two species to reproduce, a male one and female one. That means that their reproduction do not depend on an, but the reproduction depend on an square. The reproduction in malthus form, when the n dot is an, is working for bacteria or something like this. In our real life, when we consider mammals or more highly organized species, we have to take into account that we need both of them, male and female. So we have to modify the model, and we'll take into account these effects. First of all, as I said, the reproduction need male and female species. It's the first. The second, mammals have long gestation time. Gestation means the time when female is pregnant. So it is some delay between the moment between two different moments of reproduction. There are always some delay. For human, it is like the gestation time for 8 months and a few months more to recover for a female. So the equation must be in the form 11. What does A, B, and tau means? A is the average number of cups. So it's the number of children for every gestation. For human population, it is like 1 point something small, because there are not too many twins, triplets, and so on. But if we consider, for example, cats, the average number of kitten is, I think, more close to 4 or 5. Sometimes there is 1 kitten, and sometimes there can be 7 kittens. So average is more close to 3 or 4. Next, tau, it is the time of gestation. And B, the average time between successive pregnancies. So B must be greater than tau, because it is the gestation time plus some time for recovering. What does it mean? What does the right-hand side means? We can consider a function. Let f of n is ab n squared divided by b plus tau n. Let us consider two situations. The first one, when the population density is small and n is small, and another situation when n is large. We'll see what effects provide us the right-hand side of this equation. What can we see? If n is small, we can conclude that tau n is small comparing with b. So our f of n, if n is small, is approximately a n squared. We divide denominator and numerator by b. We neglect tau n, and finally we get a n squared. That means that if the population density is small, then the birth rate is n squared speed. So when the density is small, we see that the reproduction is far more small. It's quite natural. If there is a huge forest with only 2 rabbits, it's a real problem to reproduce. Maybe they will not meet at all, and so there will be no reproduction. We can see this situation in whales. There is a very small density of whales in the ocean, and the probability of meeting 2 whales is really small. That's why they have not too many kids, and so the population vanish. And what is happening if n is large? If n is large, then we can neglect b, and if n is large enough, then f of n is ab divided by tau n. AB divided by tau n. So for low population density and for high population density. So it means that at high population, there is enough free females to reproduce. As we consider the animal population, the female give birth to kids every time as she can. As more kids as she can, it's okay for animal. It is not the people who can think, do they want kids or not? The animals are so it's just an instinct, not more. Well, it is now the equation 11 is our birth rate. What about death rate? We have to take into account the mortality. So if this is our birth rate, we must take into account some negative coefficient. It is always, since the first part is always positive, we must have something negative. So let us assume that the dying probability is evenly distributed. So the coefficient C will be also a constant. So Cn is the mortality? Well, let us consider the right-hand side of the equation. Let us see when n dot is positive and when n dot is negative. So far, we'll see are there any steady states, and then we can conclude something about their stability. So if we want to find the steady states, we have to solve the equation ABN divided by B plus tau n minus Cn is 0. This one. So far, we can divide by n. So we get the first steady state. And then we have an equation ABN divided by B plus tau n is C. And after easy calculations, we multiply by B plus tau n and we arrange the summands. Finally, we get another equilibrium, n equal to CB divided by AB minus C tau quantity. Since A, B, C, and tau are all positive, then sometimes in this model, this L can become negative. But from the biological point of view, it must be positive. Otherwise, there is only one steady state, so it means that the population dies. Let us try to draw a picture of n dot. So let us draw the right-hand side of the equation. So this is the plot of our f of n. Here, the right-hand side is f of n. So what do we see? We can easily calculate it. It is not a problem. If the point L is positive, then we have following picture. Following picture. What we see? If n is more than 0 and less than L, the n dot in this region is negative. So n dot is negative. It means that the population decrease in this region. The population decrease. And starting from L, it start increasing. We can draw the solutions. We can draw the solutions of our system, and we can see that all the solutions that are starting below L, they are going to 0. They are going to 0, and the solutions that exceed L, they are increasing. Well, is this model good? Well, no ideas. But we have the same problem as Malthus equation. If our species number exceed some critical value, then the population become growing to infinity. So that's the problem. That's the problem. If n0 exceed L, then the population goes to infinity. That means we need some fixing. We need to decrease our population growth with further increase of the population. So we want to have something like this. So we need to add some new function to the right-hand side of the equation to see the decreasing of the population with high density. And this model will be okay. This model will work. A few words about our actual model. We can see that since the n dot is negative near the 0 region, we can conclude that n equal to 0, this point, the steady state, is stable. Oh, I'm sorry. Is stable since the population decreases to 0. And what about L? Is it stable or not? Will the solution remain close to L with increasing
No.
of the? Yes, we see that that L is some watershed. If population exceed L, they go away to infinity, and if the population is below L, then it goes to 0. So this cannot happen in our real life. In our real life, we always expect to see at least one stable solution, because everything that we see in the real world is have some stable point. Otherwise, the system goes to another state. We'll get another system with a stable, steady state. So, have you any ideas how can we fix this model? What should we add to the right-hand side to see our feature? So we want to see the right-hand side decreasing with large n. Have you any ideas?
To modify negative cn to negative cn squared, probably, or something.
Yes, okay, it works, but we can do better. We can add one more summand with n square. That's right. Let us consider equation in this form. We add, so we have one positive summand for fertility, one negative for mortality, this one for fertility, this one for mortality. And we add one more for competition. it means that our species with a high density start compete each other. And that's why they start fighting for resources, for females, for some living area. And finally, we can consider the model with negative dn square. The equation becomes more complex. There are 1, 2, 3, 4, 5 coefficients. 5 coefficients, and we see that it is too much. So, as usual, we introduce new variables, x and t prime, to get more simple equation. So we just change the variables and we get another equation. We can see that we can divide the right-hand side by a. It is the same for, there is the same product for every of 3 functions. And we can make 2 changes. So far, we had 5 coefficients, and finally we get only 2, C and D. We can analyze the right-hand side in the same way. So we are interested with solutions when the right-hand side is equal to 0. We get the algebraic equation of the second order. And using the technique that we had from school, we can derive that there are 3 stable states. The first one is trivial when x is equal to 0, and if x is not 0, then we get the equation of the second order that have not more than 2 solutions. So far, we have one 0 solution, and we have 2 non-trivial equilibriums if A and B are both positive. Sometimes both of them are positive, sometimes not, but we are interested in the most complex situation when there exist all 3 steady states. We can examine their stability as usual. So if the right-hand side is f of x, we can calculate f prime at x equal to equilibrium. And finally, we'll see the sign. If the sign of this f prime is negative, then the equilibrium is stable, and if it is positive, then unstable. The equilibrium is unstable. So it needs some calculations, but I can't say they are too difficult. You just calculate f prime and compare it with 0. So far, in the most interesting situation, when A and B are both positive, we can see the following picture. Let the bigger root is L, and the root that is smaller, the least one, is K. So we see that the problem from previous model is solved when the population is below K in this region, n dot is negative. So the population decrease, and it means that if the population drop down below K, then the population will die. We see it on the solutions plot. The solutions are going to zero. The zero equilibrium is stable, and as in previous case, K is unstable because our solutions are growing between K and L, and after L, the same, the solutions become decreasing. So far, we have both of these features. First of all, we see the feature of vanishing small population, and the second one is stabilizing of the population between some positive equilibrium L. So we have two stable equilibriums and one unstable here. Two stable and one unstable. This model is called the model with lower critical number, and K is the lower critical number for our population. We can see in the real life that it really happens in our real life. There are some populations that now are close to this lower critical number, and there are some populations, some existing populations. So they did not disappear yet, but we understand that they are disappearing right now. So we are trying to protect these populations. We restrict hunting. We are trying to make some protected areas for these animals. But if the population drops below lower critical number, it means that the population itself is vanishing. So we have to interact. For example, if the population can be saved in zoo with some human aid. So the species are fed, the species are cured, and so on. We are trying to do anything to save the population. Sometimes we increase the fertility with some artificial things like extracorporeal what is the right name? Extracorporeal EC, I don't remember. Well, that's the most interesting from the one species model. it have all the features we needed. Both of them, the stabilizing in some positive region and vanishing when the population drops below some region. Okay. Another way to see these features, we just simplify the equation. We introduce L and K, and if we draw a plot of this model, if we draw the right-hand side of this model, we get absolutely the same. Picture. Oh, so the picture is the same. There is a bit less biological meaning here, but the model 13 is more suitable to analyze because L and K are involved in the right-hand side, so we are not needing a lot of additional coefficients. So if for some biological model we know the lower critical value and we know the capacity of the environment L, then we can write some proper model for this population. It is called Olli equation. Olli equation. Well, another interesting model for one population. It is the problem of exhaustion of stocks. The problem was introduced by Soviet mathematician Arnold, and the idea is as following. We have some fish living in the pond. We assume that the population of our fish is described by the equation n dot is f of n. We assume that the function have two zeros. So if we write f of n here, f of 0 is 0 and f of L is 0. Between them, our function is positive, and in all our cases, it is negative. So far, for this shape of our function in the right-hand side, we can conclude that L is stable, 0 is unstable. Since n dot is positive, then the population quickly replenish. So if at some moment the population drops down L, it replenish. And the same if the population becomes bigger than L, then it is stabilizing to L. So it is okay with the fish, no problem. The population leaves, the population exists. The situation is very, very stable. So it's okay, but there is a problem because we love fish, we love eating fish, we love fishing itself. So we want to optimize the fish in this pool. There are two different strategies. First one is a rigid one. So we come to the pool and we take some fish for example, every day we take some amount of fish. So the equation with fishing will be like this. C will be our coefficient of fishing, intensity of fishing. It is the first case. And the second one, when we are trying to fish proportion with some proportion. So we'll try to fish the number Pn. If there are a lot of fish in the pool, the hunt will be bigger. And if the number is small, then we'll have not too much hunt. So the main problem is how should we act? Should we always fish the same number, or we should fish some proportion? And another question: when the number of fishing will be better, will be bigger. Okay, let's try to analyze it. Let us see. First of all, we see the shape of our function f of n. We see that it is at maximum when n equals to ns. Okay. First of all, let us consider the first regular catch. So we introduced some positive intensity C, and we are trying to optimize the C. What is the biggest possible C that can be achieved? Look at the picture at the right. It is our initial function on the right-hand side. This one. This one. C equal to 0 here. Let us try to increase C. When we increase C, the right-hand side function will decrease it is happening. So all the function goes down at n dot axis. So if we increase C, we see this picture. Here, A and B are positive, and we see that n dot is there is still some region at that moment when n dot is positive. So the population will stabilize near the point B. But if the population will drop down lower than A, then we'll get the situation from the previous model, and the population will vanish. So finally, we increase C up to C equals to f of NF. It is absolutely maximum possible C that we can achieve. when we consider the equation n dot is f of n minus f of n est, we see that the right-hand side equal to 0 if and only if n equals to n est. So if the number of fish equals to n est, then the population survive. And in all our other situations, the population will die. This is the picture of this critical situation when C is f of n est. It means that if the population is bigger, then it decreases to our steady state, and if it becomes at least below n est, at some small value below, it becomes dying. So far, what will happen with our model? Let us suppose that initial number of crucians is okay. Initial number of our fish is okay. It is bigger than this critical value. Then the population will decrease, and if something happens in the real life, always something happens. For example, at some day, the fishing will be bigger than f of n est, or maybe there will be some accident in the pool and so on. Bad weather, bad water, some disease. At some moment, the population will drop down, and then it will go to 0. That means that the hunt with some regular catch, when we are trying to optimize the regular catch, we see that the model becomes unstable. That's the main idea. Let us look at another so it's just written my words. So the point A is unstable, the point B is stable, then A and B becomes more and more close. Finally, they merge into one unstable equilibrium position. Next one. Let us consider the proportional catch or differential quota. The model takes the form f of n minus kn, and then we can draw the picture. When k is 0, we have also our initial model. So it is this shape. Then when we increase k, we get functions like this. What is optimal k? What is optimal possible k? Optimal possible k is derived from equation f of n minus kn is 0. So k is f of n divided by n. And we can see that the biggest possible k optimal, is f of n est divided by n est. So it is the biggest possible catch in our equation. The red line shows us the right-hand side of our equation at optimal k, and the left-hand side is the solutions. And we see that the population in this model stabilize near the point n est. So it is our optimal equation. So we find this point when the average multi-year income Kn crosses the curve f of n. So unlike the previous situation, we see that the new system with a feedback, the new system becomes stable. The point n est is globally stable. So for any initial n, the population of our fish will stabilize near n est. Moreover, we can see that when we are trying to catch with the proportion this k equal to f of n s divided by n s, the average income will be f of n s the same. So in both models, the average income is the same, but in one model, the system becomes unstable, and in another model, the system becomes stable. That's why when we want to take, for example, some taxes, when we want to catch some fish, or we collect some goods from our nature, we have to take into account the models with not rigid control. For example, when we consider the tax for our salary, our government take 13% from all the amount. The amount is not fixed. For example, and we understand that this control is much better than some fixed tax. For example, if the tax will be, 5,000 rubles. If your salary is small, then the tax will be too high. And if your salary is big, then the tax is too small. That's why we have to consider this dynamic feedback control. That's the main result of this model. A task for you. Consider the function f of n in this form as 1 minus n quantity product n, and calculate both of these models with the constant catch and with a proportional catch. First with this catch and second with this one, and find out that the optimal catch is 1/4. Well, that's all about fishing model. Have you any questions about it? If something is unclear, I ask you to don't worry to interrupt me and ask, because sometimes something can be difficult and unclear, and it's okay. We have enough time. We can focus on this problem and repeat a bit slower. Well, that's all about one species models. But in the real life, we understand that usually different types of species interact, and this interaction type can be different. What can be the influence types when two species interact each other? Maybe you can give me some examples from the real life. Are you here?
Yes, we can hear you, but we are thinking.
First of all, really any type of interaction, because we have no one. So let's start from something. Two different animals, how do they interact? Can this interaction be positive or negative?
First of all, the most obvious, I suppose, they may compete for the resources.
Okay, they can compete. So what does the competition means? When we have two populations, every one of them have its own equation. Every one of them have its own dynamics. And now we see that they meet each other from one and from the second population. And the interaction can be positive or negative. The first one, you said, their competition. Okay, so the different animals compete for different resources, or maybe the same resource. Give me some examples in the real life.
Different types of trees in the forest may compete for sunlight.
Yeah, exactly. Perfect. It's the first one. So the common resource, the sunlight, the space, and different types of trees really compete. Okay, another one. Different animals who feed trees, grass, and so on. Some vegan animals. they can compete for these resources. Some predators can compete for the animals they hunt. For example, lion and guepard, like this. So they can eat the same gazelle. So if there is some area where do lions live, if another type of animals come here, it is negative for both of them. So both of the populations suffer. It is the first. Another type of influence. It can be a predator-prey type of interaction when one type of species feeds on another. So the most common situation, like wolves and rabbits. So the only type of interaction between these animals, if a wolf meets a rabbit, it wants to eat a rabbit. So if we consider the biomass of wolf population and rabbits population, we see that this interaction leads to increasing of wolf biomass and decreasing of rabbits biomass. And the last one, more maybe not that common, it is symbiosis. Symbiosis. It contains three different types. The first one goes mutualism, when both of the species have some benefits from interaction. For example, there is well-known example of hippopotamus and birds that clear teeth from some junk. So it is okay for birds because they have free food, and it's okay for hippopotamus because they don't pay money for dentist. Birds do it for free. So there are some types of these interaction in the world of bacteria, in the world of trees. Sometimes different type of trees can coexist and help each other. For example, one type of tree can take some resources from the earth and produce another type of resources needed for another. So it is some chain of useful resources, and they add one another to get them. There are another type of interaction. So the first type, when both populations have benefits. In economics, for example, those who produce beer and those who produce chips, when they can unify, for example, at some advertisement, they help each other. If someone buy beer, there is a big probability that he will buy chips or some snacks. So these companies do not compete. Moreover, they help each other. Another type of interaction is called commensalism. It means that one population have benefits and it's neutral for another. There are some difficulties to give a good example. But well, maybe something in economics. Well, let's suppose that there is a company that have some unused metal, and there is another company who carries this metal and earn money from this metal. The first is doesn't have any benefits, and the second earns some money from it. So there can be some type of this interaction. Much more common situation, and amensalism. What does it mean? It is neutral for the first population and bad for another population. The main example is the human population. When there is some population in the wild nature, there is some balance in it. And when human comes to this population, a human sometimes leads to some problem for a lot of species. It is not critical for human population. It is quite neutral for human, but the existence of human itself have a lot of problem. Does a lot of problem. For example, people build a road. Maybe it's okay for human population, but it leads to some problems in the forest where the road is built. Sometimes we can see this in economics. There is a big company, something is neutral for a big company, but can be deadly for a small one. So some sort of the competition when the big company do not earn more money, but a smaller company cannot survive. So the second is competition, when both of species have deductions, not benefits. And finally, the predator-prey type of interaction, when one species feed on another. What about the equations? Alfred Lotka in 1925 and Vita Valterra in 1926, they separately introduced the model 14, the simplest model of two species interaction. Let us see what does all of these coefficients means. What is the right-hand side? For example, for first equation, n1 dot is c1 n1 plus a1 1 n1 square plus a1 2 n1 n2. Let us suppose doesn't matter who is pre and who is predator. Doesn't matter. What does all these coefficients means? So this quantity is the equation for a separate variable, or unchecked variable, where there is no interaction. And here is our interaction. So what does usually C1 and 1 means? If we come back to a previous model, we can see that C1 and 1 is our fertility and mortality, and A11 and 1 square is the intraspecific interaction, intraspecific interaction. So the interaction inside one population. And the last one, A1, 2, and 1 and 2, it is the influence of the second population to the first. So since AII and I square are responsible for intraspecific competition, the interaction is usually a competition. There is no real situations when high density provides some benefits for population. So AII is always negative or equal to 0. AII cannot be positive. What about C1 and 1 and C2 and 2? It depends on the dynamic of isolated population. First of all, we'll consider the predator pre-model and we'll see what are the signs of C1 and C2. And the same for signs for A12 and A21. What more is interesting here? What more is interesting? From the biological point of view, we have to consider only positive solutions. So if we draw a phase plane of the equation, do you remember what is the phase plane? So we have our 3D space with the time, and here we see some curve, and depending on time. And when we look at the projection to N1 and 2 space, we see another curve. We see another curve like this, starting from T1 to, for example, T2. So when the time changes, the curve goes at some trajectory. Our solution goes along this curve, and all the phase plane is covered by these trajectories. So starting with some initial values, N1, 0, and 2, 0, with increasing of the time, the solution goes somewhere else. So when we consider the phase plane, we're gonna interested only. Oh, I'm sorry. We're gonna interested only with positive quota. this one, positive quarter. What is more interesting? And these we will denote this region as n plus. N plus. What more is interesting? Let us look at the equation. Let us look at the equation. If we see that there is a product of some quantity and n1 and product of some quantity n2, and we see that the line n1 is 0 and n2 is 0, is an invariant set. So if the population becomes 0 at some moment, it will remain 0 because n dot is 0. So if at some moment n1 is 0 at time t1, then n1 is 0 for any time more than t1. It means that our curves cannot go out from n plus. So if the solution start in the region n plus, it will remain in n plus. So our curves can go to 0, can go to the border, but never can cross the border. It is very good from the biological point of view. It means that the number of rabbits will never become negative. And the number of wolves also will never become negative. That's okay. That's very, very good. So from the mathematical point of view, the positive ortant is also an invariant set. And the solutions cannot go out of this ortant. So what about the predator pre-model? We start from the simplest one. We have no self-limiting. So A11 is A22 is 0. And we assume that the first population are victims or pre, and the second are predators. First of all, we have to understand what are the coefficients. What are the signs of our coefficients? So the model is really very, very simple. And we see that it is not natural because let us consider the first equation. N1 dot is C1 plus A12 N2 N1. Let us suppose that there are no predators in our forest. There are no wolves. So we consider only this equation. So N dot is C1 N1. Therefore, if it is the only equation for our victims, we can conclude that the sign of C1 must be positive because no one eat our victims. They can replenish and their population will increase. So the sign of C1 must be positive. Next one, when we consider the same in the same way, the equation for N2, we see that in the absence of our trees, what will happen? If in the forest there are only wolves and there are no rabbits? It's quite clear that our wolves, they will die. All of them, they will die. So the coefficient C2 must be negative. First one is positive and the second one is negative. Yes, we understand that there is no self-limiting here. And if there are no wolves, the number of our rabbits will go to infinity. That is not natural, but it is the simplest model. Then a bit further, we're gonna fix it. And finally, we have coefficients A12 and A21. It reflects the intraspecific interaction. What does mean A12 and 1 and 2? The product of N1 and N2 means the probability that a wolf meets a rabbit. And what will happen when wolf meets rabbits? What's happening with the biomass? The biomass will transit from victims to predators. So if the first are victims, then the sign of A12 must be negative and the sign of A21 must be positive. So far in this equation, we have one positive and one negative function in both braces. So the right-hand side sometimes can become positive and sometimes it become negative. So far, we're gonna see some dynamics with coexistence of victims and predators. We can see this coexistence from the mathematical point of view. First of all, we have a system. And we need to analyze the steady states. First of all, what are the steady states? How many steady states can be in this system?
Two.
And what are them? Are they positive, negative? What are these steady states? To get the steady states, we have to solve the equation C1 plus A12 and 2 and 1 is 0, and C2 plus A21 and 1 and 2 is 0. the first steady state is trivial, so n n0. Let it m0 oh, m0 is 0, 0. So a trivial one. So in this model, there is no rabbits and no wolves. And if we divide by n1 and n2, we get a trivial equation that gives us n1 will be equal to negative c2 divided by a21, and from the second equation. And n2 is negative c1 divided by a12. So we got the steady states. But the main question is, what is the sign of this second steady state? We know that C2 is negative and A21 is positive. So negative and negative, the product will be positive. C1 is positive, but A12 is negative. So far, the product is also positive. So finally, in our model, we have two steady states. The first steady state is trivial one, and the second is positive. What does it mean that there is a positive steady state from biological point of view? Can you explain it?
I suppose there is some amount of wolves and rabbits which can live together to infinite time. I don't know, something like that.
That's right. So they can coexist. It means that there is some amount at which they can coexist. It is very, it's crucial for our biological meaning. It means that at least at some quantity, they can coexist. So it is, well, some globally, they can coexist. If only trivial solution will be valid, it means that there is a big probability that all the population will die. Sometimes we can expect something more complicated in mathematics, but usually if there is only one steady state, it means that they can die. Okay, let us try to analyze both of these equilibrium states. So the first one, M0, and the second, N1 and 2, with N1 and 2 calculated above. So what is the linearization? Let us linearize our right-hand side of the equation near the equilibrium positions. So if function f of n is a vector c1 plus a 1, 2, n2, n1, c2 plus a21, n1, and 2. To linearize, we have to calculate the Jacobian matrix df by dn at point n equal to m0 or m1. So it's not that hard to linearize and to get the matrix of linear approximation. So let us calculate. I think we should do it for the first time at least. So df by dn, n is a vector, so it is the first one. We calculate f1 prime with respect to n1. So it is c1 plus a12 n2. The second one, c1 n1, when we calculate derivative with respect to n2 is 0. And a12 n1 and 2, the derivative is a12 n1. Oh, yes, okay, that's right. So it is our derivatives. And the second give us a21 n2, c2 plus a21 n1. So it is the Jacobian matrix. And when we apply the point m0, so n1 is 0 and 2 is 0. Finally, the matrix is C1, 0, 0, C2. It is our Jacobian matrix. What can we conclude about this matrix? Since C1 and C2 have different signs, the eigenvalues, no, we can see that the first eigenvalue is C1 and the second eigenvalue is C2. C1 is positive, C2 is negative. So far, the point M0 is unstable. Please refresh your memories about stability theory. We will use this linearization a lot during our lections. So this singular point is called a saddle. A saddle, we have two real eigenvalues with different signs. It is a saddle. And the next one, we need to analyze the point M1. But I think we can do it on the next lection because the time is running out. So, have you any questions?
No, I don't think so.
Okay, so thank you for your patience. Today we have the practice for groups 7 and 8, so they can remain, and we'll discuss the topics for the presentations that that you will provide me. Let's make a break for 15 minutes and we'll come back.
Okay.
Mm-hmm. Okay, we can continue. What about your ideas about the topics for presentations?
So I can start. Can you hear me well?
Uh-huh.
Excuse me, I can't hear you.
Just
Now it's better. Yeah, all is okay.
mhm.
So actually, we are not sure what. Actually, we need the list of topics because we have just a few imagination and it's currently pure. Yeah. So actually, I have a friend. He said to me that he has low IQ level and he can't imagine it by himself. So he wants you to make a list of topics, and then he can decide what to choose.
Well, what are you interested in?
Yeah, actually, about me, I know what I'm interested in. For example, I have just a few topics, and maybe you can help me to choose between them.
Okay,
for example,
so you can name all of them.
yeah. For example, did you hear about NFT? It's a new token money, I guess, or something
Yeah,
like
sure.
that.
I heard about it, but for me it's a bit something. Well,
Yeah, black box.
not
Like,
that usual, but it's a perfect topic because it is real on edge. It is developing. There is some hype in this. So NFT is okay, absolutely.
yeah,
It is really interesting for everyone.
actually, I don't know anything about this, so I really know nothing. And it's interesting for me to go deeper in this topic and to find something interesting and how it works actually, because all of my friends, approximately all of my friends, are in it and they know about them and they are making money actually right now. So without any knowledge base, without any differential equations and such beautiful things like that. And it's strange actually to me.
Okay, NFT is perfect. I like it.
Yeah, what else? Let me see. It was crypto. It's related to this.
It's okay too. It's not that new as NFT, but it's okay because it's always interesting to know some more. We can discuss it. It is really interesting because some of you really believe that cryptocurrencies can be the main currency. So it can replace, for example, dollar or euro. And for me, I'm not sure. And we can discuss it. It's really interesting.
Yeah, also blockchain and all that stuff related to this. Actually, I saw a video. It was something like all of the people are related to each other. So you are my, for example, step brother in the second age. I don't know. So we are all relatives. We all are relatives. So maybe this. And actually, it connects with your lessons about rabbits and population and all that stuff.
It's interesting thing because now there are some relatively cheap study of your genome. So sequencing their genome is cheap enough. So there are some studies about about your race, about your so you just give part of your DNA and it is analyzed, and you are given some result. For example, according to your DNA, you are a white man, tall, with, for example, brown eyes, and you can compare, is it right or not? Or maybe according to your DNA, you have some of your relatives live, for example, in North Russia, some of them live, for example, in Germany. It's interesting because you even may not know about your grandfathers, and you get more information about it. Moreover, the DNA analysis can give you some important information about your health. For example, if the probability of cancer is bigger for you, so you have to pass some tests because of your DNA information. It's really interesting. It's become cheaper, and yes, you can make a good presentation from it.
Actually, it's all about me, and I have some extra questions about what we should do. So you want from us like a popular science speech for what timing actually? 15 minutes or 30, 45?
No, I think 15 or 20 minutes, not more.
20
So
minutes.
do you know what is TED Talks?
Yeah, it's a popular channel on YouTube.
Yeah. You can see some presentations on TED Talks, and yes, if you will do something similar, it's okay.
Understand. So without any formulas like analysis, like just popular speech, like.
Yes, sure. So you give usually you can give some pictures, some videos. You must have the presentation itself with the name, with some structure. It doesn't. Well, I don't know how many slides should contain your presentation, but it depends on you. Sometimes the presentation can be short, but you can say a lot about it. Sometimes not. That depends. Just do a good presentation. Imagine that all who hear you are your potential bosses on the work. So try to push yourself and to do your best, to show your best us.
Okay. And about timing, you want us to do it on Tuesday, right? Tomorrow, or maybe a bit later, because we are not actually capable of doing this.
I don't think anyone will be ready for tomorrow. So if you need more time, we can make some extra workshops, no problem. Or for example, if the time of finishing is 17:00, we can go an hour more. It's not a problem. So every one of you will have enough time to make the presentation.
Yeah, I see that we have lessons on Saturday. So as for me, it will be better to perform on Saturday.
Yes, I think we're gonna cancel the tomorrow practices and prepare for Saturday. Yes.
Yeah.
We have the same one class. We have 1.5 hours. So at least 3 of you must be ready.
Yeah.
I ask you to make a Google document.
Yep.
With all your surnames and your topics, and
time.
every one of you, yes, can fix the time when he will be ready, and we'll see all the picture.
Yeah. Okay. We will make it, of course.
And moreover, when you will prepare, you will fill this Google document with the names of the presentations, and you will see what is remaining, what is interesting. But really, the topic is up to you. I don't want to fix, for example, 30 topics and only them. Sometimes, if one of the students is interested in something specific, it is really very interesting to hear the presentation about something particular. But if you are deeply inside, if you know a lot, it's really interesting.
Okay, so that's I have no questions actually. Always understood. Oh no, one more question. As far as understood, tomorrow we will cancel our lessons, right?
Yes, I think you will not be ready, so it is senseless to meet. We can move it another day if you will need it.
Okay. Thanks.
So that's not a problem. I have a lot of time, so if we'll see that you have no time, I will extend it. No, not a problem. Absolutely. What about another topics? Space is always interesting.
Hi. Question though. I thought we were like, so we're starting presentations like next Saturday already?
Mm-hmm.
Yeah, I thought, okay. Okay, good to know. I mean, I have a topic. I wanted to talk about, I was inspired by our last lecture or last seminar / workshop. I want to talk about monorails and like maglev train systems in general. I think I have a lot to say on that, and generally I think talk about the technology and talk about the economic viability of that sort of train system in general. And I guess that would be my topic that I would like to do. I'm not sure if I'm going to be ready by Saturday though, but we'll see.
Okay, so you can write your topic in the Google document. You can upload the document in our group in MS Teams.
Okay.
It will be the best. So every one of us will see who is ready, who is not ready, what's happening. But I ask you, starting from Saturday, on every workshops there must be at least 3 who are ready. 3 of you who are ready, because otherwise nobody will be ready up to the last workshop, and it will be scrambled. Well, I don't like it.
Yeah,
So
fair.
So please self-organize yourself, okay?
Okay.
Well, maglev, yes, it's okay, it's interesting. I never drove maglev personally. Once I met high-speed trains in Europe. It was like from something like from Rome to Florence, and really the speed was 250 kilometers all the ride. It was really very quick. I was impressed.
I mean, I don't want to talk just about maglev though. I do want to talk about like standard like monorail systems, because I mean they're kind of closely knitted between them, because maglev is a form of monorail, and I do want to talk about both in general. So we'll see. We even like, I think like most major cities do have like a monorail system. Like even Moscow has a monorail line, if I'm not mistaken.
Maybe. I was not in Moscow for a long time. Yes, okay, it's up to you. It's your topic, and you can fill your presentation with anything that is interesting from your point of view. I just ask you to make the presentation better, to try to make it interesting, first of all. It should not be too scientific, but more popular.
Okay. Another question, like, but when because so like, are we presenting only like on like seminars, or are we also presenting on like Thursdays when we have like practica? Because it is a bit harder because I mean, that's a lot less time. A lot more people are gonna like go through it, and on practica there's only our group, but on seminars it's us and 307. So I was wondering how that's gonna work. Is it like 3 groups per week, or are we gonna like do more?
First of all, for me, I do not see any difference between practice and the workshops or seminars. For me, it is the same. We have lections and your presentations. It's the first. The second, I think if one group is not ready, and the number of students in a group is different. So if one group is ready and another is not ready, no problem. You can go to your mates and make the presentation at their time if they are not ready. No problem with it. For me, the main result, all of the students must make one presentation. That is the final result of this activity.
Yeah. What I'm trying to say is, just give me a second. I'm trying to like find, like, for example, like, here's the thing, because how it like turns out to be is that the amount of lectures we have in a week, well, it's very densely packed, and I do realize that we have like half a semester. But for example, like we have a seminar like on Monday, we have a seminar on Saturday, and for example, for us, we have two like practica on like Tuesday, and 307 has them on Thursday. So that's what I'm asking about specifically, is that there are a lot. Are we just going to like stick to presenting on Monday and Saturday, or are we going to include Thursday and Tuesday too?
And what is your group number?
Ours group number is 308. We're the group that has two two lessons tomorrow, and 307 has 2 on Tuesday. So
Irma, we are already 408.
4, yeah. Thank you.
Well, I'm looking for a timetable. I really don't understand how many how many seminars or practices are there in different groups, and I can't compare it with the students' number now. But well, for me, it doesn't matter. You first of all, it will be very good if you will follow the lections, because the lections are for all, and you can follow only the seminars you want. It's not a problem. Everyone will do one presentation and not more. So the attendance is up to you. If it will be interesting, yes, everyone is welcome. But if you have a lot of your own jobs, so you can make your presentation, for example, for Saturday, and you can finish with seminars.
Okay. Let's then stick to like I suggest at least for now doing like our lectures, our presentations after lectures. I think that would be best than doing it like by group on Tuesday and Thursday. I think we would prefer doing it after lectures in general, because there would be more people in general that would like be available to like do like 3 every time.
Yes, I think so. I have no ideas why the practices are divided by practices and seminars, and every year it changed. I have no ideas about it because in previous years the lections were for all groups and seminars were for all groups the same, and they were not divided. So it was a bit more easier to follow and to understand how many time do we have. But I think every one of you will have your minute of the glory to really to make the presentations.
Okay, thank you.
Okay, so I think you can start with the Google document with your topics, with the timetable when you will be ready. I think you better do a timetable for all groups. For all groups that will make the presentations. So so far all our topics will be different, and you will know who is ready and who's not, and all the timetables will be filled with presentations. I have some seminars for group 6, 7, and 8. And group number 5, it is something different, someone different.
Excuse me, Sergey Vladimirovich, could you please follow the link? I dropped it into chat. So I did a table. Like, I think it's more convenient to us to work in Google table, actually.
No, it doesn't matter.
That,
It's
yeah.
up to
So
you.
like something like this, right? If you are following.
Just a moment. Wow. Just a moment. Where is it? Where is it?
Message.
Well, I think yes, I have some problem with my tablet because it opens only this picture. Just a
I can
moment.
actually send you anywhere if you want some another place.
Well, don't
Maybe
don't worry. I will see. I will look at this, and you can send me some messages. I am available on VK, so it's not a problem. Not a problem. Don't worry. I have no ideas why I do not see it from the tablet, but and my computer now is not attached to internet, so I can see only your plates with your names.
Okay, actually, I send you in VK.
Oh, okay. Just a moment. Just a moment. Oh, I see. I see. Okay. So just fill it. I see. There are 2 NFT epigenetics. Wow. It's amazing. Well, okay. I think we discussed all we need. So see you on Saturday. Right?
Right.
Okay. Thank you.
Okay. Thank you. Goodbye.
Thank you.
Goodbye.
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 Thank you. Goodbye.